Let us start the second part of the relativistic quantum mechanics. So in the first part, we have seen that Klein-Gordon equation was plagued with two major problems due to the negative energy solution. Because of this negative energy solution, the spectrum was not stable, so it was not unbounded from below, and due to this negative energy, the probability density also becomes negative, and basically that loses the interpretation as the probability density. So, to circumvent these two problems, Dirac was actually looking for an alternative equation, or alternative wave equation to replace this Klein-Gordon equation with a better equation. So, what he noticed that in the Schrodinger equation, you have only first order time derivative and second order spatial derivative. But the rho or the probability density does not have any time derivative. Whereas in the Klein-Gordon equation, you have second order time derivative, and due to that, in the definition of rho, you have a time derivative, and that time derivative actually brings you this energy in the definition of rho. So it becomes negative when energy becomes negative. So Dirac thought that okay, to avoid this negative probability density, we need to have an wave equation which will be linear in time derivative. So he was basically looking for a wave equation with which is linear in time derivative. But if you have first order time derivative in your wave equation, since this is a relativistic wave equation, it should be consistent with the Lorentz transformation, and that requires that you also should have first order spatial derivative only. You cannot have second order derivative, spatial derivative, like in Schrodinger equation. So Dirac proposed that okay, you look this Hamiltonian linear in spatial and time derivative like this. So this alpha 1, alpha 2, alpha 3 and beta. So these are the four constants he multiplied, so that you have only linear in derivatives. So once you actually write this h psi is equal to this e psi, so basically this e, again you use this correspondence principle to write in terms of this time derivative, and this p1, p2, p3 are actually this space derivative, and this beta mc square psi x. So basically you write this in the shorthand notation that this alpha dot del, where this alpha components of this alpha vector are basically this alpha 1, alpha 2, alpha 3. So this is the Dirac equation. Okay. Now we have to find out what are this alpha I, alpha 1, alpha 2, alpha 3 and beta. Once you find this constants or the coefficients, then you have the equation, you have the full equation. And this alpha and beta has to be independent of space and time. Otherwise, it will not be consistent with Lorentz transformation. So, since this is a relativistic wave equation, so it must satisfy this relativistic energy momentum relation. So E square is equal to P square C square plus M square C to the power 4. That relation it has to satisfy. So to check that whether it satisfies this equation, you just need to square these operators on both sides in the Dirac equation, and you get this equation. So you can see that when you multiply all these things, you get this alpha 1 square del x1 square plus alpha 2 square del x2 square in this way, and so these are basically diagonal terms, and there are two types of off-diagonal terms. This is say this alpha I alpha j plus alpha j alpha I del xi and del xj. So I naught is equal to j here. Okay. And here this one derivative and this mass term, this cross terms, so that gives you this term. Now to satisfy this energy momentum relation, this E square is equal to P square C square plus M square C to the power 4, what you basically require is that this E square psi has to be equal to P square C square plus M square C to the power 4 psi. So which is nothing but the Klein-Gordon equation. So this Dirac equation, when you square all these operators, they have to satisfy Klein-Gordon equation. Okay. So if we just compare these two equations, immediately we see that this all these off diagonal terms has to be 0, and this alpha I square, because here all these coefficients are 1, so all this alpha I square has to be 1, and this M square C to the power 4 term also has the coefficient 1, so beta square has to be 1. And since these terms has to be 0, so I can actually write that this indicated in red, this has to be 0 and this term has to be 0. So basically this put the condition on the constants alpha and beta. So these are the conditions they have to satisfy, that all the alpha I square has to be 1, beta square has to be 1, and alpha I alpha j plus alpha j alpha is equal to 0 for I not is equal to j. So this basically is called the anti-commutator. In the commutator you have negative sign here, so here you have positive sign, that is called anti-commutator, and the notation for this anti-commutator is this curly bracket. So alpha I alpha j anti-commutator has to be 0, and also alpha beta plus beta alpha has to be 0. So basically alpha and beta has to anti-commute also. So you know that normal classical numbers, they commute, they cannot anti-commute. So these are not classical numbers, they cannot be ordinary numbers. So only anti-commutator, to get these anti-commutation relations, they have to be matrices. So Dirac proposed that okay, this alpha and beta are not ordinary numbers, but they are matrices. And since this Hamiltonian is Hermitian, so these matrices also has to be Hermitian. So once they become Hermitian, basically they has to be square matrix, n by n square matrix. So now we have to find 4 such matrices, linearly independent matrices, which are Hermitian and anti-commutating matrices. So there are 3 alpha and 1 beta, so total 4 such matrices we have to find out. So if you think that okay, in 2 dimension I have Pauli matrices, so these are 3 Pauli matrices, and the other independent matrix that you can think of in the 2-dimensional space is identity matrix. But identity matrix commute with everything. So you cannot find a 4th matrix which will actually anti-commute with all these sigma matrices. Okay. So in the 2 dimension, it is not possible to find 4 such anti-commutating matrices. Similarly, in 3 dimension also, you cannot find any 3 by 3 matrices, 4 such 3 by 3 matrices which will satisfy all these anti-commutation relations. And so the minimum dimension where you can actually find these 4 such matrices is 4. So n is equal to 4. So all this alpha beta are 4 by 4 matrices. So here I have written one such choices where this alpha I are 0, sigma I 0, where the sigma I are the Pauli matrices, sigma 1, sigma 2, sigma 3. And beta is actually a diagonal matrix. You remember that once you choose this one matrix to be diagonal, all other matrix has to be off diagonal, otherwise they will commute. They will not anti-commute. So at most we can actually choose one diagonal matrix and 3 other off diagonal matrix. So you may choose some alpha matrix which is diagonal and all other are off diagonal including beta. That is also another choice. You can have many such choices. So this is not unique. It is just one choice of alpha and beta. But they have to be 4 by 4 matrices. And they have to satisfy all the anti-commutation relations and hermiticity, and their norm has to be 1. So if you take the square, there should be identity. So now since alpha and beta are matrices, this wave function psi, that cannot be a single component object. Because of this matrix multiplication rule, to be consistent, psi has to be a 4 component vector, because this alpha are a 4 by alpha and beta are 4 by 4 matrices. So sigma has to be a 4 component vector, so that these matrices act on this vector. Yeah. So now once we have this 4 component vector, okay, so this psi is a 4 component object, and they all these components actually satisfy this Dirac equation. So there is some degeneracy. So they have the same energy. All these components have some same energy. So what are their actually significance? So we'll come to that point. But before that, let us look at the plane wave solution. So we look for a solution where the space-time behavior is for plane wave. So this is basically free particle solution that we are writing. So we write this psi x as omega, then e to the power I p dot x by h cross. So this is p and x are 4 vectors. So if you write in terms of e and the 3 vectors, they look like this. Where this omega is the space-time independent 4 component vector. Okay. So that is actually called the Dirac spinor. Okay. So why this name spinor will come later. So here we write this spinor omega as phi and chi, these 2 component form, where this phi and chi each are actually 2 component spinors, and they each are actually independent of space and time. Now if we just put back into the Dirac equation, so you just put this psi in the Dirac equation, so this time derivative will actually give you this e, and the space derivative will give you this p. So basically this equation simply looks like this. So I can actually write this as 2 coupled equation. So I get 2 coupled equation. One is e minus mc square phi is equal to c sigma dot p chi, and another is this e plus mc square chi is equal to c sigma dot p. So from here I can write chi in terms of this phi. Okay. So here I assume that this e is positive quantity, so that e plus mc square becomes is always a positive quantity. Now you put back this guy here in this first equation, and then what I get is that e square minus m square c to the power 4 phi is just p square c square by phi square. So here this comes because of the sigma dot p whole square is equal to p square. So I have used that in this fact. Now if you just see this operator relation, I can write a square is equal to p square c square plus m square c to the power 4, just like the Klein-Gordon equation. So energy again, both positive and negative energies are allowed, just like Klein-Gordon equation. So that problem is not resolved yet. That negative energy solutions are still allowed by Dirac equation. But for time being, let us forget about this problem with the negative energy, and let us see this what happens to the probability density. So what happens to the continuity equation of probability density? The continuity equation for Dirac spinors, again you can write in this form, where this rho is just psi Degas psi. So to basically derive this continuity equation, you know the same strategy that first you multiply with psi, and then you take the Hermitian conjugate of that equation and then multiply with psi, and then subtract these 2 equations, and then you will get this equation. Just like this Schrodinger equation or Klein-Gordon equation, you use the same strategy. And then you get this rho, which is psi Degas psi. Now psi is a 4 component vector, so I write that as psi 1, psi 2, psi 3, psi 4. These are the 4 components. Then this rho is simply just mod square of all these components, sum of all these, sum of mod square of all the components. So mod of psi 1 square plus mod of psi 2 square plus mod of psi 3 square plus mod of psi 4 square. So since this is sum of all mod square, so this is definitely a positive quantity. So now rho is all positive definite. and we don't have any problem to interpret that as probability density. So rho in the continuity equation is positive definite, and we interpret that as probability density. So Dirac got rid of the negative probability density. That problem is now resolved because of this linear, that equation is linear in time derivative. But not the negative energy. Negative energy still makes the spectrum unbounded from below, like this Klein-Gordon equation. But we will discuss how Dirac resolved this problem at the end. So till now, till that we assume that, okay, so forget about that problem and discuss about the positive energy solutions. And at the end, we'll discuss how to actually make the spectrum stable, and how actually Dirac made that spectrum stable. That we'll discuss at the end. So now, how to interpret this psi? As I told before, that psi is a 4-component vector, and all these components satisfy the Dirac equation with the same energy E. So there is some fourfold degeneracy. So what are these degeneracy? Why? What is the you can say what is the symmetry behind that degeneracy? What are these components? So to answer these questions, if you look that alpha matrices involve Pauli matrices sigma, right? We can write down this alpha matrix in terms of these Pauli matrices, and Pauli matrices we know are the spin operators for spin half particles. So H cross by 2 sigma Z, that is generally we write as the Z component of the spin half particle, right? So immediately you think that, okay, can I relate these components with the spin of the particles? So are these particles spin half particles? Are they related with the spin half particles? So let us check that. So for positive energy solution, we write this sigma. So basically this phi and chi, and we know that how to write this chi. At the very beginning, we discussed that chi has to be written like this, C sigma dot P by E plus MC square phi. So I just write that thing here. But this phi is completely arbitrary, right? Phi is not determined yet. So we may choose that phi, say 1, 0 and 0, 1. I say that this phi up and phi down. Okay. And any arbitrary 2-component vector can be expanded in this basis, in this phi up and phi down. So for a given 4 momentum, we can have only 2 linearly independent solutions for omega, for positive energy. Yes, right? So though we have these 4 components in omega, or the 4 elements, but only we have 2-fold degeneracy for positive energy. Okay. Similarly, for negative energy, we can show there are again 2-fold degeneracy. So total 4-fold degeneracy comes because of these 2-fold degeneracy in positive energy and 2-fold degeneracy in the negative energy solutions. So now consider the rest frame of the particle. So this momentum vector P is equal to 0 and the energy is mc square. So we are considering this positive energy solution. And then I write this 2 linearly independent plane wave solutions as psi 1 and psi 2. So basically this phi 1 is 1, 0. And since P is equal to 0, if we just look at this term, since this P is equal to 0, P vector is equal to 0, so these 2 components become 0. Only these 2 components are actually given by 1, 0 or 0, 1, and whatever that component is, this is 0 because of this P vector is 0. So basically I have 1, 0, 1 and 3 zeros here and 0, 1, 2 zeros. With the same energy, E is equal to mc square. Okay. But these are the eigenfunctions of the operator sigma z. I can write this actually the operator of this sigma z. I just construct this operator with this sigma z are the Pauli matrices. So if you just see that this one will have eigenvalue plus h cross by 2 for this operator, but this psi 2 will have eigenvalue minus h cross by 2. So psi plus and psi 1 and psi 2 both have same energy but different eigenvalues of sigma z with plus minus half h cross by 2. So similarly for negative eigenvalues, as I mentioned, that we can construct two linearly independent states. So here we actually had this 1 and 0 here. So similarly this 0, 0, 1, 0 and 0, 0, 0, 1. In this way, I can actually construct two other states which actually correspond to the negative energy states. And these are again the eigenvalue, eigenstates of the sigma z operator. Now we can actually generalize this capital sigma z to this sigma for the other components, say x and y components, and write these three components in this vector form like this. So these components now actually satisfy standard commutation relations for spin operator, like this sigma x sigma y is equal to I square sigma z. So this is basically the spin operators, 4-component spin operator. So this small sigma or the Pauli matrices are the 2-component spin-up particles, spinors. So for 4-component spinors, basically this capital sigma z is the spin operator. So we can see that at least in the rest frame, Dirac spinor represent spin hub particles. You can interpret those as the spin hub particles. So in the rest frame, Dirac equation describes spin hub particles, and since the spin is a fundamental property of a particle spin up in the rest frame is a spin up particle in any other frame. So we can say that Dirac equation actually describes spin hub particles or fermions. So if you just see that Dirac never intended to derive an equation for spin hub particle. He just wanted to rectify the Klein-Gordon equation, which was plagued with two big problems. So he wanted to remove those problems or resolve those problems and end up with an equation which actually describes fermions. But if this momentum not is equal to 0, then these sigma matrices are not good operators to describe spins, because it does not commute with the Hamiltonian, because it also has this alpha dot p, and this alpha and sigma has also this small sigma, and alpha also has this sigma. So these two things don't commute. So you cannot construct simultaneous eigenstate of the Hamiltonian and the sigma matrices. Okay. So you actually like to have some operator which will actually play the role of sigma as in the rest frame for any other moving frame. So that is actually done by this helicity operator. So this H is defined like this. So you can see that this sigma dot p is basically, it actually projects the spin along the direction of the motion or the direction of the momentum. So that is why it is called the helicity. And again, it will actually give two eigenvalues plus minus h cross by 2. So this omega, when acts on this by this helicity operator, actually gives you plus minus h cross by 2. Now if you just write this full form of this h, and you write this equation, and then this phi for positive helicity has to satisfy this equation, which will be sigma dot p by mod of p phi is equal to phi. So I put this phi, this plus index here or subscript here to remember that this is a positive helicity state. And for negative helicity, if you have this, pick this negative sign here, you will actually have this sign, this equation. So this phi plus and phi minus, these are two linearly independent helicity spinors you can construct. Okay, so the rest of the thing I will share in another video. the part 3 of this lecture.